So, our next and final speaker is Richard McElreath, who is a professor and director in the Department of Human Behavior, Ecology and Culture at the Max Planck Institute for Evolutionary Anthropology in Leipzig. That's quite a mouthful. So yet again, another book, Statistical Rethinking, which has been hugely widely praised. So Richard, welcome. Thank you very much for agreeing to give this talk, and I'll hand over to you.
All right. Thank you, Eleanor. And I will remember how to turn this on. Okay. Hi, everyone. I'm Richard, and I'm happy to be the fourth speaker here. I'm going to talk at the kind of higher conceptual level for my 20 minutes. And I want to start with a metaphor about teaching in a completely different subject, which is language learning. I'm an anthropologist, and one of the things anthropologists do is learn languages. It's like part of our methodology, actually, is that we learn how to learn languages. And so if we just start comparing European languages for a moment, there's this famous meme some of you will have seen, where you can compare English grammar as a little kitten to the grammars of other European languages, which are increasingly ferocious cats, and so on into other languages. German is a tiger for some reason. Turkish is a lion. And then we get into Slavic languages, and they're really quite monstrous as well. And then Finnish and Arabic will destroy your city. Right. So this is a joke, but if you're in English, if your first language is English, you recognize the point of this meme is that English has very little grammar. You've maybe started to learn this over time, and other languages have much more complicated grammars. If you're learning English as a second language as an adult, you're really happy that English has such little grammar, right? Because you can just string words together in an order and basically be understood. And it's a nice thing. The point of this, and why it's relevant statistics, is that when we learn a subject, we bring with it some set of unconscious grammar that influences how we interpret it. And when students share an unconscious grammar, or a first language, as it were, teachers will teach to that quite often, and that this will influence how we do teaching. And I think this happens nearly always with Bayesian instruction. It happens to me too. I'm just trying to get better. And there are alternatives, but here's the overview. You want to think about it. Frequentist statistics has a grammar, and Bayesian statistics has a grammar. These grammars overlap, but they're distinct and they're conceptually different. Bayes is often taught using frequentist grammar and terminology. Right? This is grammar in quotes because stats doesn't have grammar, I guess. But yeah, it has rules of composition, and it has terminology and concepts that we use to assemble models and analyses. We use terms like likelihood, which is not a Bayesian term, I will insist. And in the course of this talk, I want to try to convince you it doesn't even make sense in a Bayesian context to talk about likelihoods, really, even though we're going to continue to use them, myself included, because we live in a frequentist world for the moment. The grammar, this frequentist grammar, students really don't fully understand it themselves, right? Because they've gone through a few courses in frequentist stats, and they've kind of understood some things, right? But they still can't correctly define a p-value, right? Let's be honest, right? No, I, as a Bayesian, don't think it's possible to correctly define a p-value, but that's a discussion for a time, after I've had 3 beers. But but you know what I mean. All joking aside, it's very difficult for students even to grapple with the compositional rules of frequentist analyses. And then when they start reusing those concepts in Bayesian courses, it creates it's a new set of problems. This application and reuse of the grammar is unconscious, both on the side of students and teachers, I think, quite often. And teachers are under a lot of pressure. I teach for a living. Many of you do as well. I take it very seriously, and it's really hard, right? You think you understand a subject until you try to teach it, and then you realize you don't. Yeah, it's a very difficult thing to do. And so this naturally leads to focusing on the easiest examples because you need to scaffold the students up. So you can't start at something that's, the full Bayes. It'll just crush them. I mean, the full frequentist would crush them too, right? But they've already been through a few frequentist courses. And so teachers tend to focus on examples where Bayes and frequentism are very similar. So this is what I call the Gaussian model, right? The normal model. It's got a closed form, updating rule, lots of really nice things about it. It's a linear regression, and it's really useful. So it's something you want to teach people. But this is not very nice for teaching them what's different about Bayes, because it just reinforces the idea that they can reuse concepts from frequentist courses in this context. So I've committed all these problems myself. And like I said, I'm just trying to get better, right? And I'm not sure exactly what to do that's different. And this talk is like a confession and a request for assistance, if you will. And finally, on this slide, I think in the context of a curriculum where Bayes is, as Mina just showed, often an elective, and there's very little time and also little appetite for what would be the analogy of immersion-based language learning, where you have a course where you just say, forget frequentism. I'm not going to talk about that at all. I'm not going to compare to it. We're just going to talk Bayes. And I do this a little bit in my book. What people will joke in my book is that it takes me 200 pages to derive a linear regression, which is about correct. It really does. It takes 3 weeks and 200 pages for me to finally get them up to a linear regression. But that's the Bayesian immersion, and maybe no one really needs that. Yeah. So this is not a new observation, of course. Dennis Lindley has said everything there is to say about Bayes, probably. If you read through all of his angry letters to statistics journals, you'll find him saying everything someplace. No, I'm a big fan, but he was a very opinionated man. And so here's this is the most germane quote here. What most statisticians have is a parody of the Bayesian argument, a simplistic view that just adds a woolly prior to the sampling theory of paraphernalia. Uh, and this is, I think, a side effect of how it's taught, right? Is that you learn sampling-based theory. Instead of saying frequentism, we could say sampling-based theory. And then Bayes comes on second, and then the concepts are layered on top of it rather than relearning the language. So this is like reusing grammar of your first language in a second language. And it can function. I'm not saying it's a total disaster, but it does cause problems. And just give you a quick idea what I mean. The outside view on Bayes from sampling theory is that data have distributions, parameters don't. The likelihood is this function. It's not a probability distribution. Of course, you write down a Bayesian model, and this thing we call a likelihood is a probability distribution. And students notice this, right? And then they call me a liar, right? So this is a problem. There's this imaginary population. Yeah, I mean, the problem isn't that it's imaginary, it's that this concept doesn't necessarily exist in Bayesian updating. And this idea that Bayes is sampling theory plus priors. So like you take a standard linear regression and staple some priors on it, and now it's Bayesian, right? And that's not a very satisfying sort of thing to teach them the full power of Bayes. And then priors are subjective, and the goal is uninformative priors because those would replicate frequentist results and so on. Those of us who teach Bayes were familiar with these issues and trying to correct students away from them and so on. But the curriculum kind of encourages it, so it's hard to blame the students, right? They've flowed along into this, and they're doing their best to cope with a complicated subject. So I'm going to go quickly through some slides that are very conceptual. I don't have any detailed examples. I don't have any B's like Ben, but next time I'll come up with some B's. But I just want to talk about a couple of aspects that I think are interrelated. And the first, if we take the insider perspective on Bayes, is that these distinctions that are taught as fundamental in sampling theory statistics or frequentist statistics are not fundamental in Bayes. They emerge from interaction with a sampling design, but the distinction doesn't arises later. That is, they're logically post the design of the generative model. The one way to say this is I just think of the Bayesian approach. I think of the Bayesian approach as defining a joint generative model of all variables. And by all variables, this includes things that we might observe and things that we might not observe. And in the Bayesian approach, there's a unity among all these variables in the sense that before we've decided which have been observed or not, they're all treated the same. They all can have probability distributions. And that's illegal in frequentism, right? So, and things under one sampling design, a variable could be observed, and under another it isn't, but the same Bayesian generative model tells you how to update in both cases, right? You get a different updating rule, but the underlying model doesn't change. It's logically prior to the sampling design. And the same holds for distributions, likelihoods, and priors. A prior in one model is a likelihood in another, and vice versa. And this happens in many cases. Ben mentioned in biology, this is very common in biology where you have occupancy models, is the case that I've worked with. Okay, this is enough kind of overview. And in the teaching friction, we get lots of opportunities, I think, that a lot of us, including myself, don't always take advantage of. So in the simplest sorts of models, we want to emphasize that priors serve this function that even frequentists want, which is regularization. And this is an opportunity that's often overlooked when we use these priors, which are designed to give us the same results as a standard linear regression. And it said this is a case to say that, look, in machine learning, we don't want the standard results of linear regression either. We want ridge regression or something like that. We want to regularize. And then in what I call realistic models, this is a big tongue-in-cheek because we don't know what reality is, so I'm not prepared to argue what a realistic model is. But in models that have the difficulties of missing data and measurement errors, what I mean, likelihoods can become priors because now something hasn't been observed, but we need to impute it. And that's a very, Bayes provides a kind of, I'm going to say, automatic solution to this from a common generative model, but the coding is still hard. And that's something we have to teach, and that arises into the workflow problem of teaching as well. And then, of course, famously, in Bayesian hierarchical models, you end up with priors and priors, and then it looks like models and models, and then you don't know what a likelihood is anymore, and we're all dizzy, right? Students are reasonable in feeling a bit confused about such things. Okay, so what am I trying to say is that there's a primacy of the generative model in Bayes, and this teaching this, and that the distinction between likelihoods and priors and data and parameters emerges once we know the empirical design that we're interacting with. That has some advantages, but it's tricky to do. And reusing the term likelihood is maybe not optimal, but I'm not prepared to suggest a new term necessarily. Distribution works, but the complication that arises from this immediately, though, is that you need a workflow that supports this. It's not enough just to say, oh, here's a new word. We need to teach students, or we should teach students, I think, some way to actually develop these different stages to really represent the distinction between a generative model, a joint model of all parameters, and then the estimator, the updating rule that emerges from that. Like, how do we write code, and how do we make this work, and how do we test it? And all of those fun, actual research software engineering things that make science reliable. And these things have to go together, I think, if in the bright Bayesian future that we all imagine, we will have figured out how to merge these things together in a curriculum. Okay, quick examples. And let me try to get through this and leave as much time as possible to chat. So to reinforce this claim that I've made that the distinction between likelihoods and priors is not fundamental in Bayes, instead it's emergent. It's like you're in this position, like this kind of quantum superposition until you know what's been observed, and you don't know if the distribution is a prior or likelihood. So if I write down something like theta distributed Poisson with a rate lambda, your heuristic will lead you to believe that this is a prior because theta is usually a parameter, right? It's something that you can't observe, but it's just a symbol, right? I mean, the Greeks were people too. This is just a letter to them, right? And the ancient Greeks were just people too. And So if theta is observed, we would call this a likelihood. And if it's not observed, we call it a prior. But the logical content of the statement is the same in Bayes, even though the scientific content that we bring from the outside can be quite different, right? We want to use that in designing simulations and interventions and other things we do with the model. The point being that the generative model, the statement theta distributed Poisson lambda, is logically prior to knowing whether we've observed in a particular study theta or not. There will be cases where theta can't be observed because it's something like a rate. But if it's a Poisson variable, it's a count. And so you already are sort of on deck ready to think that maybe you could observe it. But there will be cases where it's missing. And then this statement becomes a prior that serves for imputation. Very quick example, maybe make this more interesting. I've always learned that if you put animals on slides, people will pay attention more. So here's some animals. So I want you to imagine you're doing a study in your own backyard or in the neighborhood park if you don't have a backyard. And there are some birds, some Poisson number of birds, right? And they're producing notes. This is a causal graph, right? And there's a neighborhood cat who is sometimes present in your backyard or in the park, and the cat also has an effect on the number of notes because the birds are kind of scared of the cat, right? And that modifies the number present or how much they sing. And if we were going to think about data sets generated from this, there's a generative model here, and there are a number now of different Bayesian models or statistical treatments that can arise depending upon, from a common generative model, depending upon what's observed. In the standard case we teach, including myself, we think of the processes, these arrows basically as being unobserved, and our goal is to infer them. What is the influence of the cat on the notes? What is the influence of the birds on the notes? And do they interact, right? What's the function that relates these things? And it's a kind of functional inference job. And a lot of inferential statistics is this, and rightly so, because this is a very important branch of what we do in scientific inference. So this is where we've observed the number of birds and the number of notes and whether the cat is present or not. And now we're supposed to infer, and using this data set, what is happening on these arrows. And we represent those processes with magical things that we call parameters. And we call this inference. But with the same generative model, it could be that we observe the birds, the cat, and we know the processes. Or we assume we know the processes for the sake of exploration, and we haven't observed the notes, and now this is prediction. So this is the sort of the first thing I often do in my courses is try to show students that they can use the same generative model to do predictions and forecasting as well from the same basic thing. But it's just part of, you get this, and we say we get it for free from the Bayesian machinery, but you have to teach people the workflow because it's not obvious to a psychologically well-adjusted human being how you would do this, right? And one more, what I call the imputation scenario, which is very important in a lot of fields. Say you don't know how many birds there are, or you don't know if the cat is there because the cat's in a bush and the birds don't want you to see them. You hear some notes though, and you record them, and now you're in in this position where you have to make some uncertain inference about how many birds were present and whether or not the cat is present. If you have information about the generative process, and in many cases you can do this using the same generative model that you started with, that the code is going to look different because you get into all of this imputation of discrete parameters stuff that we all love to do, right? Marginalization. It's my favorite Sunday morning recreational activity. Or God forbid, discrete sampling of parameters. It's never fun. But that's what you have to teach people. But the concept of where it comes from and then it emerges from a common generative model is the point that I'm making. And this is a thing that gets lost in Bayes when a lot of us, including myself, sometimes teach it as here's a Poisson regression. We're going to put priors on it and talk about that. So yeah, to talk about that complexity, I mean, when we get into that imputation scenario, you get into things that are real workhorse sorts of models, like occupancy models, which is the kind of thing I put on this slide, and I won't take time to explain it. But I just want to say that this is not a silly case, even though it seems like a toy case of having birds and cats and so on. These kinds of issues where you've got measurement errors on both sides of the equation, so to speak, but you really have to make an inference about things to achieve some applied goal. This is routine. I'm a member of an ecology institute here in Leipzig, in addition to being in an anthropology institute, and ecologists have crummy data. We're among friends. Can I say that? It's just like, because it's hard. It's hard to. The birds don't want you to count them, right? It's just how many birds are there. This is a tough problem. How many species are there? What's happening to their numbers? We need answers to these questions now, and we have to deal with measurement and missing data when we do it. And of course, people like me go around saying Bayes is hugely useful for this, but we need a way of teaching the Bayesian curriculum which has a reasonable path students can flow through into this with workflow examples. Yeah, so the code is monstrous, right? I'm not going to spend time on this, but if you write the occupancy model in stand code, there's a bunch of other horrors here that are really non-obvious, and it's like entering a whole new world, right, of demons. Okay, I'm going to close this up very quickly with a glimpse into what I mean by workflow, which is something I've been working on a lot lately. So this is my slide of the idealized Bayesian versus the biblically accurate Bayesian. So I mean, the idealized Bayesian inference, this, it's like Laplace or something, or the linear, or the Gaussian model. It's this simple thing. There's this updating rule. Look, we're learning, and so on. And look, I like those things. Those are great. But when you actually start doing research, doing statistics in research, you need a lot more tools. And now the angel doesn't look so great. It's like the angel from the Book of Revelation. People know this meme, right? The biblically accurate angel is this like flaming sphere with 6 wings and 1,000 eyes, right? And so this is what this joke comes from. And this is the real biblically accurate Bayesian. This is the real Bayesian workflow. You're making choices in a bunch of directions, and you backtrack, and you've got to use constraints from one part of your project to check other parts of your project. And a lot of us, myself included, don't do a great job of teaching students this. And then when they get into their own projects, it's quite paralyzing. And I want to spend the next few years of my time, and including the 3rd edition of my book, really focusing on this part of it, the workflow aspect. So here's the idealized Bayesian, right, where we've got some question and estimand. This produces some estimator, which is a Bayesian statistical model we can do updating with, that has been designed partly in light of the sample. I say in light of the sample because we need to know what's missing. Yeah, it's something about measurement error, and those are aspects of the sample and not of the generative process. And then this produces some estimates like posterior distribution, and those are summarized, and then we write it up and go to the pub or whatever. And very nice. And there's some, I mean, classroom exercises can look like this, yeah, and students can learn a lot from this. But let's start inching towards real research. And real research, where there should be a scientific theory somewhere, right? And this is where the generative model comes from, and that'll influence your estimand. The estimand needs to be compatible with the theory. Yeah, it needs to be answerable in light of the theory, and the estimator as well is designed in light of the generative model, and that includes things like unmeasured confounding and other aspects that aren't necessarily properties of the estimand, right? All that causal inference stuff. And then there's the design. Where'd the sample come from? How was sample born? Right? It's an old internet meme. And maybe we got it ourselves, in which case, hopefully we used the theory and the estimand to design it. Maybe we downloaded it. There's a bunch of relevant information there that goes into this. This is already looking a lot less nice, right? But it's reality. When we teach Bayesian workflow, there's uniquely Bayesian stuff like prior predictive checks, which is something I think everybody here emphasizes, those of us who teach. It's hard to understand priors. And one of the best ways to understand them is to simulate observations out of your model using different priors. And this is a huge, and this is a way to bring experts in too. Experts don't have beliefs about parameters, but they have beliefs about observables. And so this is a huge thing. When I collaborate with scientists, we get a lot of leverage out of this. Posterior predictives as well, we can add to the graph, and things come from those. And then there are diagnostics, right? All those R hats, and Ben talked about NF, or what did you call it, Ben? I forget, something, the effective number of parameters or something like that. And we need diagnostics, right? We do, because these Markov chains, they're out to get us. And Then there's this stuff that I emphasize in my course where we test the estimator using synthetic data. So we use the same generative model to make a synthetic data set. And then we can get synthetic estimates and we can see if the estimator could work even in principle. Often it doesn't on the first go, right? There's all these things, but this is quality assurance. And in real research projects, we need this. And it's a kind of thing we'd want to teach students to be able to do as well. And then finally, I swear I'm almost done. Estimates in the form of posterior distribution really aren't that useful. We need to do stuff with them. I mean, the causal effects, simulated interventions, usually is what that means, will often depend upon all the parameters, right? So no single parameter is an adequate summary of what we're trying to learn. And same goes for predictions. Predictions will often depend upon all aspects of the model, and we have to choose some target context. So if you're a social scientist like me, you've got to make assumptions about the age distribution of the population you're talking about and all kinds of things like that. If you're a political scientist, obviously that's true as well. Biologists face issues like this too. Okay. Yeah, so this is the summary. We're not on the left, we're on the right with the biblically accurate Bayesian, but this is the world we're in, and we should commit to teaching aspects of this flaming sphere, but also developing, I think, software assistance for people. So in the way that probabilistic programming languages like Stan have made it so that we don't have to write our own Markov chains anymore. I mean, I can't write a Markov chain that's better than what Stan does, right? It'd be foolish, the amount of time it would take me to do that. There's lots of things about workflow that could be semi-automated to reduce the time and the error that's involved in doing these things, like prior predictive checks or prior sensitivity testing. Computing marginal effects is a big one where there's a great package for this, right? For doing these things and so on. Okay, I'm going to stop there. This is my summary slide, and I thank you all for listening. And if you want to take one thing away from this, it would be nice to have a new vocabulary for teaching Bayes, but we're not going to get that. So we need some other way to think about emphasizing and communicating to students that there is something conceptually different about Bayes, and at the right times and the right projects, those conceptual differences are really powerful, and they should be reflected in the workflow because we get to reuse the generative model in different ways in different parts of the workflow to do different tasks within a Bayesian project. Okay, thanks for your indulgence.
Thank you very much, Richard. Yeah, no wonder our students get very confused when you map it out in that way. So just a final reminder, we do have a little bit of time for questions, maybe a couple of minutes. So if you want to ask Richard a question, or indeed any of the other speakers, please could you pop them in the Q&A as soon as you can, and perhaps be very useful if you've tagged to which speaker you are wanting to ask the question. Richard, one for you to start with anyway. Do you have any thoughts on what the useful commonalities are between the two, Frequentist and Bayesian, I guess, if you wanted to teach early stage undergraduate tools that help with both without pushing them into one or the other?
Ooh, it's hard to say. My perspective is that the vast majority of, but not all of frequentist methods are a subset of Bayesian methods. So in that case, of course, they're compatible. I mean, Bayesians can compute type 1 error rates. There's nothing wrong. Bayesians get to use frequencies, right? It's the injunction works. My church of Bayesianism is extremely Catholic, right? It's in the sense of universal and permissive. If you want to compute type 1 error rates, I can teach you how to do that as a Bayesian, right? That's not a problem. So that's the way I might go about it if I were going to design something like that. Yeah, there are these historical differences in what people emphasize. I think a lot of contemporary frequentist methods actually are ways to evaluate models, and the estimators, there's not really a theory of estimators in frequentism, right? I mean, lots of frequentists use Bayesian estimators, but they evaluate their long-term sampling properties. So and again, that's not necessarily incompatible with Bayes because Bayesians get to care about frequencies. Yeah, so the debates are different. So it's not a completely well-developed answer, but Yeah, I think it'd be doable. It still creates this. Yeah, I mean, it's more like, are we teaching to p-values? That's the question. And then that's not necessarily a Bayesian or frequentist issue. It's more of the sociology of where we are right now in this century. Anyway, if that's an answer. It's a good question.
Thank you. And perhaps we can finish because I'm very aware that it's now 5 o'clock. Do you have a suggestion of a good reference that teaches Bayesian statistics without the frequentist language?
Well, I have written a book that is not perfect in this regard, and it does lapse occasionally, but I have made great effort to try and do this. And in fact, my book hardly ever mentions frequentism at all. There's no complaining about it. There's very little comparison. It's just I just get underway and say, you're a scientist, you got to learn from data. Here's what we're going to do. And so it feels cringe to recommend my own book, but I'm going to do
Not at all.
it.
It's a great book.
The bonus would be there's tons of free content online on my YouTube channel, so you don't even need to buy the book. You can just go there. And I'm told these days on the internet, people can find PDFs of my book quite easily, and then I'm not going to like report you to Interpol. So
That's very generous.
but yeah, we need more books like Mina's, I think, which are aimed. Mina's book is really good, and it's aimed at a different audience. And we need different fields need different versions of that book, I think. I don't know if you agree, Mina, but I think it's like different fields have different emphases, and students have different backgrounds, and there's a real mission for people from different backgrounds to write different Bayesian books at different levels. Yeah.
Well, I now know we're just over time now, so we're going to have to call it today. So can I once again say thank you very much to the Talmo 3 for hosting us today, to our presenters for really fantastic and thought-provoking talks. But I also want to say a massive thank you to Mark Andrews for putting together this fantastic session. As I say, once again, nothing to do with me. This is all down to Mark. So thank you very much to everyone.